vibrate the tuning fork and place it on the wooden box until the paper rider flutters and falls down. Once I can observe how the paper rider is falling. So just now note down the distance between these two bridges, and that is the corresponding balancing length for that given tuning fork. So tension, that is weight equal to 1000, and for 480 Hz frequency or resonating length is 7.9, and for trial 2 it is 8.1, and take the mean value, that is 8. And the next calculate N into L. Now after that, take tuning fork of other frequency and again calculate the resonating length. Like that, take a free tuning forks of different frequencies and note down the values for resonating length, and finally calculate N into L. And once you draw a graph between 1 by N on x-axis and L on y-axis, a straight line passing through origin is obtained, and this is the second tabular form consisting of different tensions in the first column. So that means at first apply a particular weight, that is after that take a tuning fork and calculate the resonating length, and again after that change the weight. Now it is 1500 grams, and again take the resonating frequency with the same tuning fork. That means for the second tabular form, fix the frequency and change the weights and calculate the corresponding resonating lengths. Now these are the values for resonating length for different weights. So weight means mass into acceleration due to gravity, that is mass equal to 2500 into 980. So this is next one is Hall effect, and the aim of this experiment is to measure the Hall coefficient, concentration of charge carriers, and mobility. Operators. So Gauss meter, Hall probe, magnetic field, and this is the Hall effect definition, and this is the formula. Mobility of charge carriers is given by mu is equal to RH into sigma, where sigma equal to 1 by resistivity, that equal to 1 by rho. And resistivity formula, rho is equal to RA by L, where A is area of the sample, R is resistance of the sample. Coefficient of Hall, that is Hall coefficient, is equal to RH is equal to Vy by T by Bz by X, where Vy is a true Hall voltage, Bz is applied magnetic field, and Ix is strength of the current in X direction, and this is the corresponding circuit diagram. So these are the tabular forms. First one, to determine the resistivity of the sample, current Ix, voltage Vx, and this is for the determination of Hall voltage, transfer sources, without field, with field, and true voltage. And these are the model graphs, that is Ix and Vx graph. From that, this is the second graph between Ix and Vy. So 1 Tesla equal to 10 power 4 Gauss. And these are the operators. Hall effect setup. This is Hall effect setup consisting of voltage and current sides. And this is 2 coils for the application of magnetic field. And this is current supply. So by changing the current, we can apply the different magnetic fields. And this is the sample. So this is the sample. So it is either P-type or N-type material consisting of 4 ends, and these 4 ends are connected with 4 wires, 2 green and 2 red wires. And this is the gas meter. It is used to measure the magnetic field intensity. It consists of a probe. This is a probe, and by placing the probe in between these two pole pieces, we get the value for magnetic field intensity. So it shows the magnetic field intensity. Here it is 42, 45 bars. So this is the procedure how to calculate magnetic field intensity using the probe. And at first, place the sample in between these two poles. And without applying any magnetic field, first of all, connect one green wire and one red wire on the current side, and one green wire and one red wire on the voltage side. So current side consisting of 2 knobs and voltage side consisting of 2 knobs. Connect red and green wires to these 2 knobs. And this is the probe, this is the knob to change the current values. At first, place the knob in current mode and place the current value to 0.5 milliamperes. So this is 0.5 milliamperes and 5 and place the knob in voltage mode. So press the knob in the voltage side and take the corresponding voltage, that is 15 millivolts. And next, again place the knob in current side and change the value to 1 milliamperes, and this is the corresponding voltage, 30.4. So at 1 milliampere, so 30 millivolts is the voltage across the probe. This is Vx values and these are the Ix values. And draw a graph between Ix values and Vx values. So this is the curve. So the slope of this curve gives delta X by delta X gives resistance. Once you know the resistance value, from that we get rho, that is the resistivity and conductivity. Why? Because resistivity formula is equal to Ra by L and conductivity is equal to 1 by rho. So next, this is the table to determine the Hall voltage. Next, after that, change the connections and connect 2 green wires to 2 knobs on the current side and 2 red wires to 2 knobs on the voltage side. These are 2 green wires on the current side and 2 red wires on the voltage side. Now switch on the setup, and without applying the magnetic field, again place a particular value for current, that is 0.47, and take corresponding voltage, that is 0.1 millivolts. Sorry, 0.2. Okay, next change the current value to 1 milliampere and again take the corresponding voltage, that is 0.5 millivolts. So this is the current and this is the voltage without applying the magnetic field. So now take different values, take 6 or 7 readings, and after that, so with the application of the field, calculate V values for different currents. So how to apply the magnetic field? Now, first of all, switch on the current supply and increase the current value. And when current is 2 amperes, when current value is 2 amperes, so this is 2 amperes current, and the magnetic field in between these two pole poles is 2000 Gauss. So now because of the application of the current, a magnetic field is produced in between the two poles. Now our sample is in between the two pole pieces, that means it is in the magnetic field. Now change the current value and take the corresponding voltage. So this is with the application of the magnetic field. So this is the corresponding voltage at 0.48 amperes current. Next again change the current value to 1 milliampere and take the corresponding voltage. So these are the voltages with the application of the field. Now take 6 or 7 readings in the same way with the field and without field, and Vy is equal to V2 minus V1, that is V2 minus V1 gives true Hall voltage. So 3 minus 2 means 2.8 millivolts, and 6 minus 5, 6.5 minus 0.5, that is 6 millivolts. Now draw a graph between